Hello YouTube, welcome to our turbulence modeling theoretical background turbulence modeling video series. So today we're going to talk about yet another tweak to the Spalart Allmaras DES model, and again we are going to refer to the paper A New Version of DES Resistant to Ambiguous Grid Densities, same as before. Now let me jump straight into the problem since we are just continuing the paper. Okay. Alright, so now we know that refining the grid enough, I guess in the regions of free shear, it switches the LES mode on. Okay, I mean you don't refine so much that you switch on DNS, because if you recall, okay, just ignore the bottom part first. You recall this. Alright, that the DES length scale for the Spalart Allmaras model, okay, LDES equals to minimum of the LRENs and CDES delta. Okay, so for Spalart Allmaras, model, okay, the DES length scale is D tilde, and you'll have D for the Reynolds average Navier-Stokes length scale, and then otherwise you will have this CDES delta, right? So if you refine your grid, your delta becomes really small. Okay, delta becomes small, and destruction term becomes big, right? So if your destruction term becomes big, okay, this is a eddy viscosity destruction term, or the SA variable, to be more exact, Spalart Allmaras variable nu tilde. Okay, so when you refine your grid excessively, I mean you refine your grid enough, you refine your grid enough and you get far enough away from the wall such that this becomes smaller than this, then your LES model should switch on, right? If your delta isn't too small. But if your delta becomes too small, and then your Spalart Allmaras variable tilde, the destruction term becomes really big, and it almost becomes like a DNS mode. Okay, DNS mode means no turbulent viscosity. I mean the other place that we destroy, okay, we destroy I mean we rightly should destroy let's see. All right, so we destroy viscosity. We destroy viscosity when D tilde is small. Okay, we destroy eddy viscosity when D tilde is small. So when D approaches 0, D tilde approaches 0, okay, we don't nu T approaches 0 as well. So where does this usually happen? Well, this usually happens at the wall, right? Recall near the wall. Okay, your D is reaching 0, right? Yes, your D is approaching 0. So your D tilde, because you have a value where D is smaller than CDES delta. Let's zoom in. You have a D tilde approach. You have D less than CDES delta, so you when d approaches 0, d tilde also approaches 0, because remember it's a minimum function, right? So when you go near the wall, your d close to 0 and your new t should also approach 0. So this is correct behavior, right? This is behavior you want, because near the wall there's a viscous sublayer. Now the other problem with this is okay, let's say you refine the grid, right? We are saying that you refine the grid. Okay, so let's say in your free shear region, right? You have a free shear region. Free shear region, and okay, you want to refine the grid. Okay, you refine the grid, so you make your delta small. When you make your delta small, because this delta is based on the volume of the grid here, when you make this delta very, very small, you also cause d tilde to reach 0, right? You cause d tilde to reach 0, and that behavior, it seems as if it's a wall behavior. Okay, so when you refine the grid too much, you actually get yourself into the wall behavior. Now, this is actually still okay. Okay, so this problem is still okay. It's still okay if and only if, so I just do an IFF there, if and only if there are, or rather I'll just say if. I don't know if it's if and only if. So it's still okay if you have enough eddies, right? Enough eddies. Alright, if you have enough eddies to compensate, because it kind of resolves, then you just have a DNS kind of a limit. Meaning to say that as your turbulent viscosity drops, your resolved eddies kind of fill in the gap to simulate that turbulence properly. This is okay. Now what if you don't have enough eddies? Alright? If you don't have enough eddies, and you have this refinement situation, you don't have enough eddies or flow instabilities. Alright? Then you have a low Reynolds number case. This is what I call a low Reynolds number case. And what happens is that not enough viscosity. Okay, you again have this moderate stress depletion, right? Because you behave as if you're going near the wall. Okay, but this low Reynolds number is not enough to generate eddies. Okay, it's not enough to generate eddies. Alright, pardon the handwriting. Yeah, but you have a model stress depletion where, again, your new T drops artificially, right? Your new T drops artificially, and well, there's no way for your flow to compensate for that loss in turbulence, because the modeled loss in turbulence suddenly disappears, and your Reynolds number locally is not enough to generate all the flow instabilities you need to make up for this loss. It's again very similar to this model stress depletion, except now it can happen not just in the boundary layer but in the free shear zone. So what can we do about this thing, right? Because when you remember, the idea is that if this filter width or this delta approaches 0, you start behaving as if you are near the wall, right? So okay, so as if it's near a wall. So delta 0, okay, let me just write this down. Delta approaching 0 means behavior as if it's near a wall. So you don't want this to happen, right? Or rather, you have CDES delta equals to, goes to 0. So delta goes to 0 is the same as CDS delta going to 0. So what can we do about this? How can we prevent, okay, CDS delta from approaching 0 in free shear regions where there is excessive refinement? Okay, how can we prevent this from approaching 0 when there's excessive refinement, i.e. Delta approaching 0? Okay, so there's this idea that in the paper it was discussed. Okay, so we use a booster function. What's this booster function? Okay, of course the delta can't actually go to 0, it just becomes very, very small. So small and finite. Okay, what's this booster function? Or I like to call it booster because it artificially increases the value of this. So psi is this booster function. Okay, psi is the booster function. Is the booster function where, okay, you increase the value of this value such that it is more than, let's say, D, for example. Hey, wait. Oh? Okay, you don't make it more than D. Okay, wrong. You don't make it more than D such that it is not approaching 0 and destroys eddy viscosity as if it were near a wall. So when I say booster function, the typical value of psi, okay, it should be greater or equal, GEQ greater or equal to 1. So when the psi is equals to 1 means there's no correction at all. But if you have this excessive grid refinement, this psi should be more than 1. In fact, many times of that. I don't know. Yeah, it should be more than 1 to correct for this grid refinement problem in the low Reynolds number region. Okay, so where you have this model stress depletion like phenomena. So psi, okay, should be greater than 1. So this should activate in, okay, 2 conditions. Okay, low Reynolds number. When I say low Reynolds number, it means it's just not enough to generate the turbulent flow disturbances. It doesn't mean it's laminar. Okay, so it should activate in low Reynolds number regions. Not enough turbulence or flow disturbances generated to compensate for loss in ut, and it should activate far from wall, i.e. free shear. It should be active only in the free shear region. So this is what this booster function does. Okay, so your new DES length scale will be as such, or rather your LES length scale should be as such. So it will be as such, and this is known as the low Reynolds number correction. Alright, how should we decide? How should we design this booster function? Okay, well, the basic principle is this. Basic principle. Okay, so we have it such that the subgrid stress model should behave like we calibrate it. Okay, we calibrate psi such that the subgrid stress model, or this is actually like the new T, the turbulent viscosity, so to speak. This new T model should behave like a Smagorinsky model in the free shear zone, even in low Reynolds number. This is the basic principle. So what's the Smagorinsky model? Just some flashback, some throwback. So nu T equals to C, okay, Smagorinsky times delta squared, okay, times the mean strain rate, mean rate of strain. Okay, I'm not going to go through that again. Okay, so this is the basic principle. So lots, I'm not going to show you the algebra, I'm just going to show you the final result. So lots of math later. Okay, you do your substitution, what have you, but it's basically this principle. We want to calibrate. Okay, calibrate, that's a new word. Calibrate. Yeah, we calibrate, so after lots of math and calibration, such that this psi should make the whole model behave like a Smagorinsky model in the free shear zone. So lots of math later, we find that psi looks like this. Psi squared equals to, alright, Fw divided by Fw star. I'll tell you what these constants are in a little while. Okay, so CB1. Okay, so most of these actually, Fw and CB1, these are actually from the Spalart Allmaras model. Okay, so if you're not sure what CB1, CW1, all these are, please go to the CFD website. You can see this Spalart Allmaras model. They will use the same definitions here. So for example, you have Fw, you have G, you have Ft1, Ft2, CB1, CW1, so on and so forth. Okay, so you have all your constants here. So except for Fw star. Fw star actually takes a new meaning. It's a new thing that this paper came up with. Alright, so let me type this 1 minus Ft2. Okay, so I'm just copying from the paper. You'll be able to find it online. And the denominator is this Fv1. Okay, 1 minus Ft2. Alright, so this is what the psi square looks like. Okay, and now what is this Fw star? Fw star is actually equals to 0.424. It's just a constant calibration. Okay, and the rest of the constants, okay, for the rest of constants, please refer to the Spalart Allmaras model, to Spalart Allmaras Rand's model, and this is where you'll find it. From the, you can Google it online, CFD online website, it's all in the description. Okay, so and what they found out, okay, so now you have the underlying numerical underlying first principle generation of this. Okay, now we tweak it numerically. Okay, now we make approximations to tweak psi square or psi numerically. What do I mean by tweak it numerically? It means I want to give it make it easier for it to calculate and make it well behaved, so that this thing doesn't suddenly shoot to infinity or something. So that's what we mean. Okay, anyway, so for this, okay, psi will kick in kicks in when there should be some meaningful amount of eddy viscosity. So this is the principal behind psi square, okay? But what is this meaningful amount of eddy viscosity? You know, this eddy viscosity, it should be more than nu divided by 10. Okay, anything below that means that this eddy viscosity is almost negligible. It's getting to the negligible zone. Anything above, then you kind of start to have to take it into account a little bit more seriously. So in this range, you find that we find that there's a nice simplification we can make. We find that this actually, okay, we find that this is equals to, was approximately equals to 1, okay, plus minus 2%. So that's a great thing. Means we can get rid of some calculations that we don't want to solve for. So whenever you see this 1 here, this is because we approximated this as this, okay? You make that approximation. Okay, so now we also want to make sure the bottom kind of doesn't reach 0. Okay, we want to make sure psi square doesn't blow up. Psi square doesn't blow up and reach because the denominator reaches 0. So one of the things that can reach 0 is this 1 minus ft2, right? Because very far away from the wall, ft2 will become 1. So what is ft2? Okay, ft2 is this thing over here. Okay, so far from the wall. Okay, far from the wall, you have chi. Chi is the ratio of this Spalart Allmaras turbulence viscosity, so to speak, over the natural, the fluid viscosity. As you go very far away from the wall, ft2 rapidly approaches to 0 because this exponential becomes a negative a big number, right? Exponential negative a big number would, hold on, sorry. Exponential minus a big number would result in ft2 becoming 0. That's still okay. Now the thing is that if you have a very, very low turbulence viscosity, if you have a very, very low turbulence viscosity, that means nu tilde approaches 0. Nu tilde approaching 0 means chi approaches 0. Chi approaching 0 means ft2 approaches 1, right? So nu t approaches to 0 means chi approaches 0. So chi equals to nu t divided by nu. And so ft2 means ft2 approaches to 1. Okay, because remember what's ft2? ft2 equals to the following. It is some constant ct3 exponential minus ct4 chi square. Okay, so if this approaches 1, then this term will become very, very small. Alright, so this term becomes very, very small. So you don't want it to be so small that it causes numerical instabilities. So you put a cap. So you say you want a maximum, okay, of these two numbers, so that if this ever reaches 0, you can actually put a cap to how low it goes. So what's the cap? Okay, the cap in the paper used was 10 to the power of minus 10. So this prevents this term from reaching 0 in the case of extremely, extremely low turbulence viscosity, which is what happens in our grid refining case, because you refine your grid so much that you destroy all the turbulent viscosity and it can reach 0. So You don't want that to happen, and this kind of helps it become stable. And of course, there's another reason why you probably want to do this. It's because you still want, I mean, if you refine your grid high enough, you still want it to cause, you want it to be having proper behavior in the DNS zone. What do you mean? What do I mean by DNS zone? It means that when you refine your grid so much, you cannot have this thing blow up. Okay, that's one of the things. So yeah, so that's why you have this max function. Another way to limit, okay, another way to cap psi is simply with this. Okay, so you have minimum of, okay, so this is another reason why you want to cap psi. So it's properly behaved, and it doesn't exponentially go up so much. So it's 10 square, which is basically 100, and then you have this function. So you cap psi square at 10 square. So okay, this makes it such that psi actually goes from 1 to 10. So this limits psi to go from 1 to 10. So this is how the booster function, so to speak, behaves, and this is actually the low Reynolds number correction. Okay, so I mean, of course, you can apply both principles. I mean, you can apply this principle even to the DES version. You can also apply this principle to DES version of K omega SST. You can apply it to the K omega SST DES. Okay. You can apply it to K omega SST DES. You will basically have the same principles going on here. Alright, but I'm not going to do too much of discussion of that here. I'm going to stop here and say, yeah, this is basically the low Reynolds number correction for the Spalart Allmaras DES model. So this is why you will see, for example, in the OpenFOAM user guide, you will have this low Reynolds number correction here. So this is what this function is here for. Hopefully this video has given you meaning to all these numbers that you see, and hopefully the numbers don't scare you off anymore. All right, so you can actually make sense of these equations now. Okay, one more thing before I go. I actually forgot to mention this. You can also apply, and you probably need to apply this to Spalart Allmaras DDES. We just did our delay detached-eddy simulation. So how do we actually use this in the detached-eddy simulation? Well, remember in DDES we have an extra variable, okay, FD, to correct the MSD model stress depletion phenomenon. All right, so that can also appear inside this booster function as well. Okay, this can also appear in psi. All right, and what is this? How can it appear in psi? Remember, we have this psi square, okay, and each of these are a function. Okay, these are a function of chi. So these are functions of chi. So for instance, in the paper it describes this. Everywhere you see chi, replace it with max of chi 20 FD. So this adopts this function for the DDES version. Okay, you can adopt this for the Spalart Allmaras DDES version by applying this inside the booster function. All right. So this is what makes it applicable to DDES as well, Spalart Allmaras DDES, and that makes it on the whole more robust. Okay, so this is the low Reynolds number correction. Okay, so yeah, now is really the end of the video. Thank you for watching. I'll see you guys next time. Bye bye.